Good morning, everyone. Welcome at our first lecture from Problem Solving and Decision Making. My name is Katarzyna Wójcik. I'm working in the Computational Systems Department at Krakow University of Economics in Poland. And today I will have pleasure to have this lecture for you. Today we've got 2 hours, and mainly our today meeting will be some theoretical background for problem solving and decision making. And today we will focus on system theory. So some basically what constructs the environment for problem solving and decision making. There is few of you. I would like to ask you, maybe on the chat, or you can, if it's possible, you can use your microphones. I don't know the group, I don't know the background. I know that you are from different universities, from different fields of study, different backgrounds. So at the beginning, I would like to have like some basic knowledge about your background. You can write either on the chat or raise your hand, and I will give you time to share your background with me. Basically, what I would like to know, what is your major? What is your field of study? At what level are you studying? And what is your knowledge about programming, systems, and machine learning? I've seen one hand rise, so please, you can share the information with us.
Evelyn. I'm from Greece. I've almost been accepted as a PhD student at Ionian University. My main interest and research is the sustainability of academic spin-offs in Greece, innovation and entrepreneurship. My bachelor was at business administration in the Open University of Cyprus. And then I studied my master at the University of Piraeus in economics of education and management of educational organizations. So I gained a knowledge about the expected benefits from the implementation of EPR systems, information system security, data protection issues, but I don't have any knowledge about programming and machine learning, etc. And I'm very pleased that I have to attend this course. So I believe that I will learn enough things from this course in programming. Thank you very much.
Thank you very much. Thank you. I see the second hand rising, so please.
Hello, good morning. My name is George Fanzis. I'm also from Greece, and this is my first year in the Ionian University. I'm in the field of informatics. I don't have very much knowledge since this is my first year, but I've learned quite a lot the past months and from the Erasmus project, so that's about it from my knowledge.
Thank you very much. Anyone else want to share their background? Yes, please.
Hello, I'm Andrea Hugyák, and I'm a student of the Hungarian Participant University, and I learn also artificial intelligence in practice. This is a 1 long year study and give a very nice overview about the topics, but the practical approach of this course is very good additional for me. Basically, I'm an economist, engineer, and photographer, and I'm deal with the website development. So this topic is very important for me. Thank you very much.
Thank you very much. Anyone else want to share with us their background? Okay. Thank you very much for those of you who shared with your voice and those who used chat for this. I see many people with economic background, which corresponds to our topic, because problem solving and decision making is connected to economics, definitely. But also nowadays it is connected to different machine learning and artificial intelligence methods, which can support a decision-making process. So I will start the lecture with the system theory, because every decision that is made within some system. Okay, probably it will be better if I will turn this off so you can focus on my presentation, and I will share my screen with you. I hope it will work. I hope you can see my screen.
Yes, everything is okay.
Okay, thank you for the feedback. So problem solving and decision making with artificial intelligence and machine learning methods and tools. This presentation was prepared mainly by Professor Paweł Lula, which is my supervisor. Maybe some of you already had some classes with him, because he also had to have 2 courses within this this project. Within this this course, I'm going to mention such topics as system theory and systems analysis, system modeling, decision-making support systems, artificial intelligence and machine learning models supporting decision-making process. Today, as I already mentioned, mostly theory. I will do my best to cover system theory, system analysis, and system modeling topics. So next week, we can move on to some practical examples of models that are useful in supporting decision-making process in organizations. So moving to system theory. There are many different definitions what system is. On this slide, we have a few of them from different perspectives. So are regularly interacting or independent group of items, for example, a group of body organs, a group of related natural objects or forces, a group of devices of artificial objects, and so on and so forth. What is common for those definitions is the word group of something. Sorry, if you have any questions, do not hesitate to ask them. Sorry, I'm not sure. Okay, yeah, I think it was just the microphone problem. Okay. So going back to system definition. So the key word here is a group of something. So some kind of structure, organized society, organized or established procedure. These are the main description of what system is. Moving on to the first definition in more details. So a regularly interacting or independent group of items forming a unified whole. This can mean a lot of things. So system, according to this definition, like group of items. It can mean a lot of things. So we can have the system, well, items can also be human beings. So some social system, but it can also mean a computer system in which components of computer system interact. They work sometimes independently, sometimes as a whole. They interact. It can also mean some organization, which is also a system, because we've got employees interacting with themselves, but also with some external units, external items. So this is quite a good definition of a system as a group of items forming a unified whole. So in organization, in a company, we've got this frames within which the organization works. So we've got employees and we've got the external part that organization interacts with. And it can be seen at this slide, a kind of system visualization in which system are the elements like these dots. This is a form of a graph that depicts the system, but also the connections between them. Of course, not all the elements are connected with each other, but usually there is a finite number of steps between two units. And this is like in a whole world, but also in a system. So we can probably always connect two elements of the system in some way. And the system has its boundary. So something is within the system, but also there is a world outside of it. And of course, the system can interact with the external world. All system elements have their attributes, describing them, describing their features. And usually within one system, the attributes for each element should be the same. They will have only different values. So we should be able to describe elements of the system using some set of attributes common for all the elements. But also different system elements can make some actions within. They interact with other elements, but also, as I mentioned, sometimes with external units. So they are characterized by attributes, but they also can perform some actions. And by performing the actions, they usually aiming to realize some goals within this system. So if they exist within some structure, they must have their goal, their purpose, why they exist and why they function within this system. And also the system itself has its goals. And it is important when we've got like many elements in the system to align the goals of different elements with the goal of the system. So the units, the elements within the system should work by achieving their goals to achieve the system goal. Yes, I see a hand.
Thank you very much. Would you be so kind as to give some example about the system from a life?
Okay.
Imagine the structure. Thank you very much.
With the attributes and actions, this is what you mean, like that the system in this form. Okay, the closest to me probably would be that kind of system would be probably university system, let's say. At university, that can be treated as a system. We've got different elements, items, which are basically when we focus on human beings, for example, we've got teachers, we've got administrative employees, we've got students that can be described with their own attributes. And they are interacting with each other. And they all have their goals. Because basically, teachers' goal is to teach, to share their knowledge with students who come to university to gain the knowledge. And there are also administrative employees who will basically are there to help with the process, but also to organize the some formal stuff, for example, at universities. And they've got their different goals. They interact with each other. But university itself also has some goal to succeed in some field. And this is not only by teaching, but also by some scientific research. So all the parties involved should work to reach this goal. This is probably the closest to me, and probably to you, because as university students, this is also the structure that you could relate to. And we said that there are interactions between different elements, different units, and there is a flow of like 3 types of flow. First of all, energy, information, and materials. These are the 3 elements that are exchanged between different elements of a system. There is something what is called a synergy effect. And yes, any questions? If there was a question I couldn't understand, it was very quiet. I'm sorry. If you have questions, please maybe write it on the chat, because I wasn't able to hear it. Okay, the synergy effect. The interaction or cooperation of 2 or more organizations, substances, or other items to produce, sometimes they can produce a combined effect that is greater, that is the sum of their separate effects. We know this phenomenon. So synergy is a state in which 2 or more things work together in a particularly fruitful way to produce effect even greater than the sum of their individual effects. And it also can be expressed as the whole is greater than the sum of the parts. And how it relates to system. We said that a system is a group of items. So basically, the idea behind every system is to use this synergy effect. If we combine the efforts of units, we can get something bigger. So cooperating, exchanging energy, exchanging information, exchanging materials should help us to produce something bigger than we can do individually. So having the system, having the support of the whole system will help us to become bigger, to become something greater, also for the whole system. There are different types of systems according to many different criteria. In this case, the criteria is communication between system and its environment. I mentioned a few times that elements of the system interact not only with each other, but also with some external units. We can have open system and closed system. In open system, there is an interaction with the external world. So we've got the environment of the system, we've got its boundary, and when we've got some inputs from outside and we produce outputs to the outside world, we can say that we've got an open system. But of course, we can have closed system in which we don't accept any input from outside and we don't communicate any outputs outside. So these are the two types of system, taking communication with environment as a criteria. But even in a closed system, usually there is at least flow of energy. Even if we don't exchange materials, even if we don't exchange information with outside world, we usually exchange energy. So there is third type of system, which is called isolated system, in which we don't exchange even energy with the outside. So this is like completely isolated from the outside world system, from the outside world system. System can have a different size, but also different complexity, different number of elements within the system. And sometimes, especially for bigger systems, they are like too big to be managed as a whole. And then there is a need to create or just identify the subsystems. What does the energy mean in this context? I'm trying to think if this is mentioned somewhere later in the presentation, not to be Okay, I think that this concept is explained later, but to answer your question, what means energy? Basically, we can talk about different types of energy here. Usually a system like it was mentioned, the elements in the system exchange information and materials, which is some maybe not always physical, but it's something that we can see or hear, let's say, because when we exchange materials, it's something physical. When we exchange information, usually it has either written or verbal form, while the energy is something more difficult to catch, to picture, because it doesn't have a physical form. So it's not something that we can see or hear, but it influences the interactions between elements within system and outside of the system. I will check if I have like the bigger, a better description for this. Because we can speak about the energy in terms of physics. Basically, when we hear energy, this is something what comes to our minds firstly. So the physics, the energy. And basically, at this stage, probably I would stay with the definition that energy will mean anything that is not material, that doesn't that is not material or information at this point, but definitely it has to be, and it will be defined more precisely later with the details when we will analyze the system and when we'll talk about modeling of the system. I think at this stage this will be probably the best definition I can provide for this, because energy will be defined different for different systems also. When we are talking about the system in general, as I said, physics, but also exchange of energy in some social sciences background. There can be like different meanings in a different areas. Yeah, so to move forward, for now, let's say that energy will be everything that is not material, that is not an information. And it will be precisely described later when we will talk about in details about some specific systems. So system and subsystems. If system is big enough, usually because it comes with the size, it can be divided, or we can identify some homogeneous subsystems within it, which are not units. They also gather units from the system, but they are not the systems themselves. They are kind of subsystems. Some system can also function within a bigger, like, suprasystem. For example, for universities, it can be like the whole system of science and education in particular country. But also it is a part of a bigger system for European Union and for the whole world. So we've got the system like university that is a part of a larger system that can also interact with other system. We can present system in two ways. We can present it as a black box. We know the concept of the black box from different areas. When we've got input, the black box, so something happens inside, we have no idea what, and then we've got some output. But we can also present a system in the form of white box. where everything is clear and shown to the other world. So we've got input. We know how the system works because in white box we've got the precise information. What are the processes, how they are working, and then we've got the output of the system. As I mentioned, different system classification. With respect to its origin, we can distinguish two types of systems, natural systems and artificial systems. Artificial systems are of course created by human beings. Universities, organizations are kind of artificial systems. But we can have also natural systems which were not created by human beings. They were formed naturally. We can find them especially in biology, in some natural sciences, because they are formed then. And often artificial systems, they are created in a way that they resemble the natural systems. Also within our classes, our course, we will learn about ways of mimicking natural system by artificial ones. With respect to the form of existence, we can have physical systems. Well, physical maybe is not the perfect word here. Systems existing in reality. And we can have conceptual systems, some abstract systems that don't exist. They were invented. Maybe they were used to present something, but they don't exist in reality. With respect to the variability in time, we've got static systems that don't change with time and dynamic systems that can change with time. With respect to their form of description, deterministic and probabilistic. What deterministic means? It means that for the same input, we always get the same output. So we know how the system works exactly. With probabilistic systems, there are probabilities what may happen, but it's just the probability, not certainly if something happens, then this will be the result. There is a probability that something or something else will happen. With respect to their relationships with environment, we already mentioned it, open, closed, and isolated. We already described these three types of systems. System complexity describes the number of elements and relationships in the system. Warren Weaver defined two forms of complexity. Disorganized complexity, elements behave and interact randomly, and organized complexity, so behaviors and interactions are correlated with each other. Let's maybe get back in time to the history of system concept, because it may enlighten us more about the theory system. It was Aristotle who said that the whole is more than a sum of its parts. And this is a good summary of what system is, of what we already said, especially with the synergy effect. The whole is more than a sum of its parts. So we can see that the roots of system definitions are far back in the ancient world. Then Gottfried Wilhelm Leibniz wrote a manuscript about monadology. Monad, simple element. So the analysis, the science about elements, simple elements. This was the next moment in time when we can think about systems. Then physics, the area of physics. Nicolas Leonard Sandi Carnot, the model of a heat engine. So a thermodynamic system that is connected to physics, mostly. Then also theory of thermodynamics, so roots in physics, Rudolf Clausius introduced the concept of entropy. And entropy is something that we see also in information sciences. But it has its roots in thermodynamics, usually considered as a measure of the system's disorder. So something is not as it should be. So the concept origins from thermodynamics, but it was later implemented also in information sciences. Then we've got Ludwig von Bertalanffy, who was the founder of the general system theory. So he described what we are talking about today during this course in a form of general system theory, as we can see the cover of the book. This picture resembles the integrated circuit, so it definitely had something to do with computers, with information technology. Then we've got Norbert Wiener, the founder of cybernetics. Cybernetics is like the ancestor for computer science. So before we had computers like we have today, there was science that was interested in information technologies, and this was cybernetics. The next person who was important for the systems theory is Ross Ashby, English psychiatrist, who was a pioneer in cybernetics. He formulated the original principle of self-organization in 1947. This theory deals with how global coordination within a system can result out of the local interactions between member parts. So basically, the influence of outside of environment on the system. Then in 1943, the first model of artificial neuron was introduced. As I told you, there are natural systems and artificial ones. And often artificial ones are based on some new natural ones. In this case, we've got neural network. Neural network, which is a system. Artificial neural network is based on the natural one, the one we've got as human beings in our organisms. Like all living organisms have the the neural systems. So the artificial one, the one we used in artificial intelligence, in machine learning, is based on a natural human neuron. Next important year, 1958, perceptron is a model for classification task proposed by Frank Rosenblatt. So perceptron neural networks, artificial neural networks, and this particular type of neural network is a model for classification task. Within machine learning, within different data analysis, data mining tasks, classification is one of them, is assigning objects to certain classes. And for this purpose, perceptron neural networks are one of the best solutions. Then in 1982, we've got Cohonen networks, which are designed for unsupervised learning. For example, for cluster analysis. Cluster analysis, similar to classification, in both methods, we want to group objects. But in classification, we know what should be the structure of the sample, what classes we have, and we've got the learning sample in which we've got objects assigned to them. While in cluster analysis, we don't know how many groups we have. We don't know what are the characteristics. We are just trying to analyze the set and distinguish how many and what type of clusters, groups of objects we will have. Then we've got genetic algorithms. So once again, we are the artificial systems are learning from natural ones. John Henry Holland worked on complex adaptive systems, and he was a pioneer in genetic algorithms. So algorithms that that are based on genetics. Let's move on to methods of system description. We can have different systems. We already classified them according to many criteria. And we can describe them in many different ways. First, mathematical equations. Of course, not every system can be described in a form of mathematical equations, but certainly some of them can, especially the artificial ones. We need to have, if we are creating some artificial system, we need to have a way to describe it. And mathematical equations, sometimes very complex, are one of those methods. A very good way of describing systems are graphs and nets. We said the system is a group of units, group of entities with their connections, with their relations, especially within the system, but also outside of it. So structures like graphs or nets are perfect for this because we've got nodes that can represent the units, but also the whole systems. And we've got edges that represent the connections between them. In IT, especially in the theoretical approach to IT, we've got formal automata concepts. We can use them to describe computer systems, how they work, the theory of automata. In this case, we've got finite state machine, as far as I'm concerned. Yeah, finite state automata with stack. So this is also a way how can we describe a system as we've got states, we've got inputs, we've got outputs. So the formal way of representing a system. Another way is our Markov chains, in which we also have initial states, we've got final states, and in this case, we've got some probabilities that are assigned to each edge. Hidden Markov chains. When we've got some hidden connection or dependency between inputs and outputs, which are also a way of picturing the system structure. Structural equation modeling. Which also is a way, more advanced once again, of picturing kind of type of system. Each step we see is more complex, more specific, because in graphs we've got just nodes and edges, but the more advanced, the more specific elements we can find on the method of representing the system. We've got something what is called ontologies. Ontology is a formal explicit specification of a shared conceptualization. So basically, it's an abstract model of a part of the world. Explicit specification means it's machine readable and understandable. Shared implies and based on some consensus. So we all understand it in the same way. Conceptualization is expressed in terms of concepts and properties. At the beginning, when we described the system, we depicted units, some entities, with their attributes, with their actions, connected with some relationships. In this case, ontology can be a way to describe a system. In ontology, we've got concepts with their features and with their relationships with other concepts. Ontology is a graph-like structure. So once again, something what is based on graph, when we've got nodes and edges that represents the connections between nodes. In this case, we've got a planet that contains oceans and continents. Continents can contain, for example, lakes. Ocean covers bays, gulfs. Bays and gulfs are connected to the sea. So we can describe a part of reality using concepts characteristic for it and relationships between those concepts. So also one of the ways to describe a system. We already mentioned Kohonen neural networks. So one of the ways of describing system will be Kohonen maps, self-organizing maps, so-called, in which we've got input layer and the output. In this case, we've got some let's say, graphical representation of the structure of the analyzed data set. And it also can be used to describe the system, its structure. There is a there is a typo in the title. Hierarchical self-organizing maps. So like in this case, like Kohonen maps, but with hierarchical structure. So we've got not only one layer, but we've got many layers of the self-organizing maps. Then we've got genetic algorithms that also can describe the working of some system. In this case, we can see the concepts that we know from biology, from genetics. So genes, chromosomes, population. We've got network. We've got generations. So something we know from biology. The networks can reproduce. We've got some genetic diversity. We've got selection, like natural selection. So this system is based on, this way of picturing the system is based on some natural sciences, biology sciences. So when we know what system is and how we can describe it, let's move on to the topic of system analysis. System analysis is the process of studying an activity, typically by mathematical means, in order to define its goals or purposes and to discover operations and procedures for accomplishing them most efficiently. So system analysis will aim to describe the structure, the procedures, the goals of a system. In Business Dictionary, so relating to business, system analysis will be a general methodology that applies systems perspective by taking all aspects of the situation into account. While in narrow sense, it will be the analysis of current and future roles of proposed computer system in organization. So in this narrow sense, we've got like direct connection to computer systems. While in broad sense, we've got a system as a general in all its aspects. Where we can use systems analysis in this broader meaning. Well, first of all, we identify systems in natural environments, so natural sciences. In biology, we analyze different systems, different biology systems. In social sciences, we've got psychology, sociology, economics, management, logistics. In all these areas, we can have different systems that we can analyze in a different way. We also have in technical sciences information systems that can be analyzed. Focusing on information system, Information system is a combination of hardware, software, infrastructure, and trained personnel organized to facilitate planning, control, coordination, and decision-making in organization. In Polish language that I can refer to, we've got two separate concepts, let's say, of system in this context. We've got something what is called actually information system, which doesn't require the usage of computer sciences, which means the system, for example, in an organization, of exchanging information, mostly, as it was mentioned at the beginning, materials, information, energy. So information system is for exchange of the information. And we've got separate concept for, let's say, IT system, information technology system. So the information system supported with the usage of IT. And then we have this hardware, software, and infrastructure that is used to support the exchange of information between different units, different entities. But in this presentation, we will based on this definition. So information system as a combination of hardware, software, infrastructure, and trained personnel organized to facilitate, in our case, especially decision-making in organization. What are the main goals of information systems? They should facilitate planning in organization, planning tasks, so defining goals, all actions that are connected to making plans for the future in organization. Then we've got control, because somehow we need to check at what stage of reaching the goals we are, how the organization is functioning, if everything goes smoothly or if there are some problems. Coordination. System is complex structure. So it is important to coordinate the actions, the relationships, the interactions between different units. And decision-making. So this what is especially important from the point of view of this course. So information systems should support management in decision-making. Information systems should give the managers information that is crucial for effective decision-making. So information systems should support organization activity, all activities within organization. And that's why, like I said, in Polish language, we have different terms for information system in general, because every organization has some information system. So the system of exchanging information, of planning, controlling, coordination, and decision-making. At least it should have. But not all organizations have this system supported with information technology. So with some hardware, software, infrastructure, and other tools that will help with it. What are the main components of information system at as it was described. Well, first of all, it was already mentioned: software, hardware, and people. And this is obvious for us, that if we got information system, we've got, well, hardware, the material part, software, something that helps us in let's say execution of a tasks for this information system. We've got probably the weakest part of the system, humans, who are a part of the system in some way. But also information system, the two very important parts of information systems are processes and data. Processes describe the, they should describe the information flow within organization, the procedures that are within organization. And data, nowadays, information, but in computer system, we cannot store information directly. Computers basically work on data. So we need to model information to be able to present them in a form of data that can be stored, exchanged, presented by computer systems. So these are nowadays very important parts of information systems. Hardware, software, people, but also processes. So how it is all organized, and data that are stored, analyzed, and that are actually the way of storing information, which are the basis of decision making. Okay, what are the main reasons why information systems, understood as a computer aided information systems, are important? First of all, they allow us to store more information, and we've got easier access to information. Definitely, computers have better performance than doing the same manually. They allow to reduce costs. They allow stronger control over the system, support for new products and services, and improved services. So there are many advantages of introducing information system within organization. And some of them also help in effective decision making and problem solving within organization. Better performance, more information, especially more information. Information is crucial in decision making. Basically, in an ideal situation, we would have full information in some area to make effective decision. Of course, usually it's not possible. But the more information, the more useful information, because we can have also something like information overload when we've got too much information. But usually, if we have more information, we can make better decisions. Focusing on the factors that have impact on IT projects. So when we want to introduce the information system that will support our organization in everyday's actions, we need to take some internal and external factors into consideration. Focusing on internal factors, definitely very important thing is existing systems and data. Because usually organizations have already some systems, some databases, some applications that it uses for everyday operations. And when we want to introduce a new system, we need to take into consideration how data was stored, what kind of data we have access to. We need to also take into consideration our information technology department. So if we have a manpower within our organization to introduce a new system, user requests, so what our user needs. Basically, by users here, we mean employees who will use this system. Top managers, which are also usually benefactors of the information system. And strategic plan for our organization. These are the internal factors that we need to take into consideration while we want to introduce a new information system in organization. But also, we need to take into consideration external factors, like the government, so some legislation issues, the economy, if it's a good time for big investment, because usually introducing information system is a big investment. Our competitors and customers, our suppliers, and of course, available technology. So these are all the factors that we need to take into consideration when we want to introduce new information system in organization. But what if new information system is needed? We've got something like feasibility analysis. Feasible, capable of being done, reasonable, suitable. These are the definitions of feasibility. So feasibility analysis is the analysis if we can manage to introduce new information system in organization. And within feasibility study, we have 4 types of analysis. First of all, economic feasibility. For example, if we can afford introducing new system. Technical feasibility. If we have infrastructure, what we would have to change in our infrastructure in order to introduce a new system. Operational feasibility. So if we have a manpower and if we have employees that will be able to operate a new system, if we can integrate the new information system with our existing information system in organization. And schedule feasibility. So if, let's say, we have time, or in what time we can introduce a new information system in organization. Operational feasibility means that a proposed system will be used effectively after it has been developed. If users have difficulty with new system, it will not produce expected benefits. The project should be supported by the management. Maybe it will be needed to reduce the workforce, because if we introduce more advanced information system, it may cover more operations than the previous one, for example, and it may mean that some employees won't be, maybe not the employees, but their positions won't be needed anymore. Are the users involved in the process of system development? And is the project coherent with organization goals and main activities? We've started this course with goals. We defined system, we defined entities goals and the system goal. So introducing new information system should always support the organizational goal. So operational feasibility, very, very important analysis. For example, if employees won't be willing to use the new system, it won't bring the expected results. Technical feasibility. As I mentioned, it refers to some technical resources needed to develop, purchase, install, or operate the system. So definitely hardware, software, but also if we have in our organization experts in IT field that will be able to even maintain the system, or we will have to, for example, pay also for maintenance. Will it be possible to expand the system in the future? Or we will have to once again change it for a new one. These are all factors that need to be taken into consideration when we are analyzing if we can introduce new information system. Economic feasibility means that the projected benefits of the proposed system should overweight the estimated costs. That also includes a support and maintenance cost, as well as acquisition costs. So we need to make the economic analysis if we can afford first, but also if it will be beneficial for us. If we can, for example, reduce some cost using the system, or will it, for example, generate more costs than it will reduce? And it's not a good idea to make this change. And how the resources consumption looks over the system life. Of course, a lot of money is spent even before we install the software. Because mainly we need to pay for the system before we start using it. So the costs are going up through the whole process of system development till installation day. Then we've got some decrease in costs, but with time, when we use the system in the organization, then there comes a time when we require some major changes from different reasons. Sometimes it's business reasons, so something in organization changes, and sometimes there are technology changes. Technology is developing constantly, so we may need or may want to use new, different technology that might be better. And then probably there always is a decision if we want to maintain the old system or we want to introduce one, what will cost us more. So definitely at the beginning, we need to pay a lot of money and also a lot of time, because it's not only money, but also time that is consumed while the system is developed and installed. Then the resources are not so needed anymore. But there will come a time when we will have to once again invest both money and time in our system. So we've got schedule feasibility, means that the project can be implemented in an acceptable time frame. So at this, let's say, stage, the system analyst must consider the interaction between time and cost. Time, schedule feasibility, cost, economic feasibility. System development life cycle. Basically, usually we start with identifying problem, opportunities, and objectives. So no matter if we have already some information system in organization or not, we identify some problems, also some opportunities and objectives. The next step is determining human information requirements. So basically analysis of existing information systems, but not in the meaning of the computer systems we are using, but who requires what kind of information, what is the information flow between different entities within system. Then we need to analyze system needs. So what new system must include? What must be implemented in new system? When we know all of this, we can design the system. So first the project, then implementation, so developing and documenting software. Then we need to test it before we will implement it. And the next stage is implementing and evaluating the system we installed. So this is the system development life cycle from the moment we let's say figure out that we have some problem or there is some opportunity on the market, for example, or we have a need for a new system, to the moment when we implement the system and evaluate if it actually meets all our needs. We can also describe it. Here is a very similar schema for system development life cycle. Different probably names, but still we've got planning, analyzing, designing, developing, implementation, and maintenance. Sorry, 1 second. Sorry for this short interruption. I'm in my office at university, and somebody had a question important. So going back here, very similar steps. In previous one, we've got maintaining with testing, which is actually rather maintaining after implementation. So before we implement a system, we need to test it. And then after it is implemented, we have to maintain it somehow. Another system development life cycle diagram. Once again, more complex, but we can figure out some common steps in all three diagrams. So analysis, we always start with analyzing why we need a new system, what are the system requirements, then planning, different order, but we've got both steps. Design, so first come project, then the development. So first we need to figure out how to do it, what we need to do, and then we can start coding it. Definitely testing, if everything is as it should be. Deployment, so implementation, different way of saying implementation. So we deploy a new system. Maintenance. Here we also have evaluating. So here we've got evaluation. And sadly, the last step on this system development lifecycle, disposal. Because every system someday must come to an end. So it is no more useful for organization. So it needs to be replaced by by newer system. What are the different approaches in system development? And there are many different approaches to developing information computer systems. Waterfall model, structured approach, object-oriented approach, and agile approach. Let's start with probably the most classic one, which is waterfall model. As you can see, those models, at least the classic one, corresponds to the system lifecycle. So we've got requirements, design, implementation, verification, maintenance. Very similar stages. We start with collecting the requirements, so planning, analysis. We've got the design, we've got its implementation, verification, if everything works as it should, and then comes maintenance of the software. Structured approach, basically the two of the mentioned approaches, structured approach and object-oriented approach, are not actually the models of developing a new software, but rather models of software. So not how to develop software, what are the stages, but what is the structure of the software. In structured approach, the system is represented in terms of data and the processes that act upon data. So very, I would say, old approach in which programs are algorithms plus data structures. In this case, the programs were usually executed in, let's say, linear way. So we've got some data structures that we used that represented information that we want to store in our system. We've got algorithms that described what the system should do. And this constituted programs in structured approach. And the structured approach is realized with the use of waterfall model. So we've got business case, user requirements, system specification. So the first step, the analysis, planning. Then we've got design of the whole system and of single components. Then we've got the development phase when we construct system based on the design. Testing, implementation. So as we can see, also linear model, waterfall model for developing structured approach program. However, this wasn't sufficient for very complex software that allows to help the organization in creating effective information systems that will reflect the structure of the organization, its complexity. So object-oriented approach to programming was introduced. With all of its complexity, let's say. We've got classes that represents group of objects from a real world with their attributes and actions. So once again, we go back to the beginning of the course when we said that the system is built of elements, entities with their attributes and actions. So it is better reflected in object-oriented approach. Organization as a system can be better reflected in a computer system that is coded using object-oriented approach. We've got objects that represent single object of class. We've got encapsulation, abstraction, inheritance, and polymorphism. So some phenomena characteristic for object-oriented approach in programming. Not everything is visible and accessible for everyone. Classes can hide their insides to protect them from the outside, let's say, world. We can have inheritance, so we can base one class on another. We can have like different types of similar phenomena. So a lot of possibilities and different approach to creating computer information systems. Object-oriented analysis and design is a popular technical approach for analyzing and designing application, system, or business by applying object-oriented programming. It views information systems as a collection of interacting objects that work together to accomplish tasks. So in object-oriented approach, the organization is treated as a system. So the object-oriented application better reflects the organization structure that is treated as a system. In object-oriented analysis and design, we have many different types of diagrams that can help us to design the system. We can have, for example, use case diagrams that describes how users will interact with the system. So what users need from the system. When we have use case diagram for each use case, so for each interaction of user with the system, we can describe it in the form of scenario. Having use case diagrams and use case scenarios, we can derive activity diagrams for use cases and sequence diagrams. The next step would be creating class diagrams. So we have to analyze the system structure. What kind of classes will we have in our system? What will be their attributes? What will be their actions that they can perform? The next step will be state chart diagrams. And when we have them, we can adjust them, specify them. And then the next step will be development and documenting the system. So in object-oriented analysis and design, we can use different diagrams, usually UML, so Unified Modeling Language diagrams, which were designed to help us model the system. When we treat organization as a system, we already mentioned it. We've got some inputs and some outputs, but the main purpose of the system is to realize its goals. Different maybe not different. Okay, the organization can be seen as a system from different perspectives. On this slide, we've got different departments in organization, like purchasing, production, marketing, distribution, and finance. And this depicts how marketing manager view the organization. So basically, he sees himself in the center as the element that connects production, distribution, and finances. But how the production manager will see the organization? Of course, production in the center, connecting distribution, purchasing, and finance. So different perspective, even within organization, may influence the structure of the system. So it is important while designing information system for organization to, from one perspective, take all different perspectives into consideration, but also to find the solution to integrate them in one system. Information system can be seen as a subsystem within organization system. So it once again corresponds with these two ideas that I already mentioned and two different terms we use in Polish language. So information systems, system and information technology, let's say system. Because organization itself is a system. That operates within some environment with suppliers, customers, competitors, stockholders, regulatory agencies, and so on. But within organization, it is not that information system will cover all of the aspects of organization. So information system will definitely process, classify, arrange, calculate data within it with some inputs, outputs, and feedback, but it doesn't cover all the operations of organization. So it's kind of subsystem within organization system, which aim is to facilitate operation of organization, especially in our case, decision making. When we are talking about the information system development, it is important to mention agile approach. Agile software development refers to a group of software development methodologies based on iterative development, where requirements and solutions evolve through collaborations within self-organizing cross-functional teams. Many people think that agile approach means no rules, no documentation, we just go with the flow. It is not exactly how it works. Especially with object-oriented approach, because when we've got structural approach, usually we've got some data structures and we've got some algorithm that must be implemented. That's it. But object-oriented approach, in object-oriented approach, we've got often many different layers in application that can be designed and developed independently. Moreover, the contemporary applications are often not one big monolith, but they contain small modules that can be designed and developed independently. So agile software development helps us to organize the way how we will create our software, maybe without a strict time frame for each component, but still there must be some budget, there must be some time frame for the whole application. It's more that we decide which part of application we will do first, which we will do second last, and so on, then that there is no time frame, no budget, no deadlines. They are still, even in agile approach, but we can decide more flexible about the order, how we will, in which order we will develop certain functionalities. The 4 important values for agile approach are communication. So to be able to work more flexible, we need to have a good communication. Simplicity, feedback, and courage. We need feedback, like with the communication. Communication rather within the group, feedback from the customer. In agile approach, we often produce partially working systems. So for example, one module that we can show to our customer, we can get a feedback, and then when we are working on next modules, next components, then we can take this feedback into consideration. We have some basis on which we can move on with the project. So as we can see with this circle lines here, the agile approach is based on iterations. So we don't have like this waterfall that we plan everything, design everything, develop everything, and implement everything at the same time. Agile methods are iterational. So for example, for one module, we perform all the stages. Then we've got feedback from customer, and we can either modify the existing model or adapt it to customer needs, or we can move on to the next module, which we also have to plan, design, develop, and implement. So at the development and production stages, we've got iterations, which usually involves feedback from customer. So once again, it doesn't mean that there is no planning. There still is planning. We still have a budget. We still have a schedule. But next to requirements and the results of analysis, we also have a user review feedback that allows us to adapt system to user needs. So comparing waterfall to agile approach, in waterfall model, we've got like linear path from conception through initiation, analysis, design, construction, testing to deployment. While in agile, well, we still start from conception and we will still end with deployment, but the initiation, analysis, design, construction, and testing phases will be repeated for example, for different modules, but also sometimes for the same module iteratively. So not the linear we've got some feedback, some circle in this case. Managing a system project. Project management is the practice of initiating, planning, executing, controlling, and closing the work of a team to achieve specific goals and meet specific success criteria at a specific time. Project is a temporary endeavor designed to produce a unique product, service, or result with a defined beginning and end, undertaken to meet unique goals and objectives. So basically, introducing a new information system in organization is a project that can be managed within this organization. What are the 4 project constraints? Some of them I already mentioned with the system development. We've got scope, project size, goals, and requirements. Definitely, we've got time, tasks duration, dependencies, critical path. We've got resources, people, equipment, materials. And we've got money, costs, contingencies, and profit. These are the 4 constraints that always have to be taken into consideration in managing every project. Project management consists of 4 let's say elements. Project planning is identification of all project tasks and estimating the completion time and cost of each task. So we are planning the work within our project. Project scheduling is somehow connected to it because it means creation of project timetable, showing different tasks, dependencies between them, critical tasks that may delay the project. So everything related with time. Project monitoring is guiding, supervising, and coordinating the project team's workload. Project manager must monitor the progress, evaluate the results, sometimes even take some corrective actions. If, for example, something goes in a wrong way. Project reporting. Regular progress of reporting to management, users, and the project team itself. So it is important to report, especially to supervisors, but also to other stakeholders, what is the progress with the project. So for example, we've got identification of tasks and their costs, money, workload, time. These are all costs of the project. We've got project scheduling, for example, Gantt chart that shows us the project schedule, which task we can do after which, what are the deadlines, the time frame for each task, and so on. Critical path method, invented in 1950. It is used for complex project management. So we've got a list of tasks and their dependencies. So we've got like here, task number, description, duration, so how long will it take, but also predecessor task. So we cannot start this task, for example, before the previous task or certain task won't be finished. And we can draw a chart that will show us what is the path. In this case, we've got like starting from here, we've got two parallel paths. One of them also parallels here. And for each of them, we've got their duration. So we can calculate how much time we need and which, for example, task is critical for our project. And in this case, we've got depicted that this is the critical path for this project. We can also combine Gantt chart with the critical path. In this case, we've got tasks. We know how long which task it will take, and we've got also predecessors. To solve many of these problems, not only in working system, but also when we are developing it, designing and developing, we can use different machine learning and artificial intelligence methods. Because, for example, to create this model of tasks, when we've got task, duration, predecessor task, we can use many different methods. In this case, we've got some network model with the critical path also depicted on it. When we've got some states, some schema for this model, we can analyze what is the earliest time when we can finish the project, at which stages we can have some delays. We can count the optimistic and pessimistic realization time. What are the acceptable delays in the project? And what is the, once again, the critical path in our project? Another method, I'm looking at the time. We got like 4 minutes left. I hope it will be one of the last methods. If not, we will finish with it. And we will continue. I think rather short part is left from this. Then some short introduction to different methods and models that we will use in decision making, and definitely some practice. So PERT, Program Evaluation and Review Technique, that was invented in 1957. For every task, 4 types of time are defined: optimistic time, pessimistic time, most likely time, and expected time calculated according to following formula. So once again, a method that allows us to manage the schedule of the project. We've got tasks, we've got times, and for each task we've got expected time. And once again, the network with the realization time equals to 50 units, time units. For each project, we can calculate the variance of realization time and the total variance of the project, which is sum of variances of nodes located on the critical path. The higher the variance, the higher the risk of the project. So when we've got the critical path and there will be some delays, it is the risk for the project. So the higher the variance, the higher the risk of the project. Here we've got example of calculating the total variance for the project and then we need to determine if this is high or low risk for taking this project. The project realization time resembles the normal distribution with mean and standard deviation. So usually this is the model that is used for determining the time for the project. Okay, probably we can finish at this slide. There is few more slides, but probably I will sum up some of them. We've got, I think, 8 hours left with our course. The lecture will be recorded, definitely. At some stage also, I need to probably adjust the presentation to the project requirements with the logos and so on. And I will discuss it with the organizer, with the leading partner, if we are going to share with you the presentations and in what form, but definitely the course will be recorded. Okay, if you have any questions, we don't have much time for them. But we are seeing each other next week, and then we will definitely continue shortly with theoretical introduction. I would like to focus on some methods that we can use. In supporting decision making and problem solving within systems. So thank you very much for your participation in this course. If you have any questions, probably the best idea will be to save them for the next week or write me the questions via email, then I can answer during our next meeting. Have a nice day, have a nice week, and see you next week.